name is 5G network architecture and functions. Topics that we are going to cover in this course are 1. 5G introduction, 2nd. Use cases, 3rd. 5G system, 4th. Architecture concept, 5th. Reference point system architecture, 6th. Service-based system architecture, 7th. Network function. Let's start with the introduction of 5G in context to 4G. 5G has been introduction within the release 15 versions of the 3GPP specifications, whereas 4G was introduced within release 8. The radio access network belonging to 4G is known as long-term evolution, whereas the RAN belonging to 5G is known as new radio. NR has been standardized to allow tight networking with LTE. Tight interworking supports the interconnection of LTE and NR base stations. These base stations can then be used in combination to serve the population of user equipment. 5G network architectures based upon tight interworking between LTE and NR are known as non-standalone. Non-standalone architectures allow a smooth and relatively simple evolution towards a complete end-to-end 5G system. Non-standalone architectures allows reuse of existing LTE base stations and existing 4G core networks. In general, a software upgrade is sufficient to allow interworking with a set of NR base stations. Standalone NR base stations provide connectivity to a 5G core network. The combination of NR base station and 5G core network is known as a 5G system. The benefits of 5G are maximized when using a 5G system. Congestion within the lower operating bands combined with the requirement of wider channel bandwidths has led to the specification of both low and high operating bands for 5G. Release 15 has adopted the use of frequency range 1, that is 450 MHz to 6 GHz, and frequency range 2, that is 24.25 GHz to 52.60 GHz. Frequency range 1 supports channel bandwidths from 5 to 100 MHz, whereas frequency range 2 supports channel bandwidth from 50 to 400 MHz. Frequency range 1 includes operating bands which support frequency division duplexing, time division duplexing, supplemental downlink, and supplemental uplink, whereas frequency range 2 supports only TDD. 3GPP has specified mechanism to allow dynamic changes to the uplink and downlink transmission pattern used by TDD. Subcarrier spacings of 15, 30 and 60 kHz are supported within frequency range 1, while subcarrier spacings of 60, 120 and 240 kHz are supported within frequency range 2. The 240 kHz subcarrier spacing is only used for the transmission of synchronization signals and the physical broadcast channel. Smaller subcarrier spacings have longer symbol duration, which allows support for larger cell ranges. Larger subcarrier spacings have shorter symbol durations, which allows support for lower latencies. Beamforming and multiple MIMO are important for both the uplink and downlink of the NR air interface. These can be combined within the context of massive MIMO. Beamforming is particularly important to improve the link budget when using frequency range 2. Multi-user MIMO can be used to improve spectrum efficiency when UE have sufficient spatial separation. Both 4G and 5G have been designed to support packet switched services. 4G supports the speech service using voice over LTE, also known as VoLTE, whereas 5G supports the speech service using voice over NR, also called VoNR. 4G network supports single radio voice call continuity (SRVCC) to allow inter-system handover towards the circuit switched domain belonging to either 3G or 2G. Release 15 does not support SRVCC for 5G, but packet switched inter-system handovers from 5G to 4G are possible. SRVCC from 5G to 3G is specified within the Release 16 version of the 3GPP specifications. Our next topic is use cases. 3GPP has adopted the set of use cases identified by the Radio Communication Sector of International Telecommunication Union. These use cases are applicable to technologies being developed to support the requirements of international mobile telecommunications for 2020 and beyond. The set of use cases are enhanced mobile broadband, eMBB, ultra reliable and low latency communication, URLLC, massive machine type communication, MMTC. 3GPP is accounting for the requirements for these use cases when standardizing 5G. Release 15 focuses upon the eMBB and URLLC categories, but additional capabilities for MMTC will be added in Release 16. The Narrowband Internet of Things (NB IoT) and LTE machine technologies belonging to 4G provide a solution for MMTC within the timescale of Release 15. Each use case category has its own set of requirements. For example, eMBB requires high connection throughputs and high network capacity, whereas URLLC requires low latency and high reliability for devices with both low and high mobility. The ITUR has identified a general set of requirements and has assigned an importance to each requirement for each use case. These requirements and their importance are summarized in first figure. Requirements also vary within a specific use case category. For example, deploying eMBB across a rural area requires a focus upon coverage, whereas deploying eMBB across an urban area requires a focus upon capacity. Each use case category includes many individual applications. Examples of these applications are shown in second figure. Existing applications are included, for example, voice service, video streaming, internet browsing, social media, and instant messenger applications. Many emerging applications are also included, for example, automatic vehicles, remote control, home automation, smart city application, wearables, monitors, and sensors. Many applications require components from multiple use case categories. For example, virtual reality requires low latency to provide responsive and high mobile broadband throughputs for the rapid transfer of content. 3GPP is ensuring that 5G has sufficient flexibility and capability to address the adverse set of requirements belonging to this broad range of applications. 5G technology is driven by 8 specification requirements. Those are: first, up to 10 Gbps data rate is more than 10 to 100 times speed improvement over 4G and 4.5G networks. Second, 1 millisecond latency. Third, 1000 times bandwidth per unit area. Fourth, up to 100 times number of connected devices per unit area compared with 4G LTE. Fifth, 99.999% availability. Sixth, 100% coverage. Seventh, 90% reduction in network energy usage. 8. Up to 10-year battery life for low-power IoT devices. One of the key issues with the 5G requirements is that there are many different interested parties involved, each wanting their own needs to be met by the new 5G wireless system. This leads to the fact that not all the requirements form a coherent list. As a result of these widely varying requirements for 5G, many anticipate that the new wireless system will be an umbrella that enables a number of different radio access networks to operate together, each meeting a set of needs. As very high data download and ultra low latency requirements do not easily sit with low data rate and long battery lifetimes, it is likely that different radio access networks will be needed for each of these requirements. Accordingly, it is likely that various combinations of a subset of the overall list of requirements will be supported when and where it matters for the 5G wireless system. Our next topic is 5G systems. The 5G system include the 5G core network, the 5G access network, and the user equipment. Here the figure on the screen illustrates these components belonging to the 5G system. The 5G core network provides connectivity to the internet and to application servers. The 5G access network can be a 3GPP next generation radio access network or a non-3GPP access network. A 3GPP next generation radio access network can be based upon any of the following options. Those are: first, standalone new radio NR base station. Second, standalone long-term evolution LTE base station upgrade to allow connections to the 5G core network. Third, non-standalone base station using NR as the anchor and LTE as an extension. A new radio base station is known as G-Node B, whereas the LTE base station which has been upgraded to allow connectivity with the 5G core network is known as an enhanced E-Node B or a next generation E-Node B. For example of non-3GPP access network is wireless local area network, that is WLAN, based upon Wi-Fi. Non-3GPP access networks use a non-3GPP interworking functions N3IWF to allow connectivity with 5G core network. The N3IWF supports 3GPP interfaces towards the 5G core network and non-3GPP interface towards the non-3GPP access network. 3GPP has specified both reference point and service-based architecture for the 5G system. Our next topic is architecture concepts. Let's get into the topic. The reference point architecture is based upon a set of network elements NE which use point-to-point interfaces to interconnect those network elements. Signaling procedures are specified for each point-to-point interface. The reference point architecture can lead to repetition within the specifications if the same signaling procedure is used across multiple interfaces. The service-based architecture replaces the set of network elements with a set of network functions NF. Each network function can provide services to other network functions. That is, each network function is a service provider. The point-to-point interface are replaced by a common bus which interconnects all network functions. Services are specified for the network function providing them rather than for each pair of providing and consuming network function. An important characteristic of the 5G system architecture is the separation of user plane and control plane functions. This differs from the original 4G system architecture. For example, the packet gateway belonging to the original 4G evolved packet core EPC provides both control plane and user plane functions. For example, it provides the control plane function of IP address allocation and it provides the user plane function of packet forwarding. The 5G system architecture includes the session management function SMF for IP address allocation and the user plane function UPF for packet forwarding, that is, control plane and user plane functions are separated. User plane and control plane separation allows independent scaling of the two functions. For example, operators can add more user plane capability without having an add more control plane capability. It also allows different deployment strategies to be adopted for the user plane and control plane. For example, user plane function could be distributed while control plane function could be centralized. Distributing the user plane functions help to keep them located geographically close to the access network and so help to minimize latency. Our next topic is reference point system architecture. The 5G system reference point architecture as shown on the screen This architecture specifies a set of network elements and a set of point-to-point interfaces which interconnect those network elements. The functionality associated with each network element is described separately later on. Here the figure on the screen shows the separation of the user plane and control plane functions. Uplink user plane data is transferred from the UE to the 5G access network. It is then transferred through one or more user plane function UPF before being forwarded to an external data network. For example, the internet or a private corporate network. Downlink user plane data follows the same path but in the opposite direction. These are expectations to the separation of user plane and control plane functions. For example, user plane data belonging to the short message service SMS can be transferred using non-access stratum NAS signaling between the UE and access and mobility management function AMF. The SMS function is not shown in figure but it can be connected to the AMF using an N20 interface. The point-to-point interfaces connecting the network elements are labeled as N1, N2, N3, etc. These interfaces are known as reference points within 3GPP. Example, N3 is the reference point between the 5G access network and the user plane function. N1 is the reference point between the UE and the access and mobility management function. This reference point is typically shown as a direct logical connection between the UE and AMF. Figure shows the connection passing through the 5G access network to highlight that all signaling between the UE and AMF is transferred through the access network. The N9 reference point is used to interconnect user plane functions. A first UPF can be deployed to provide connectivity to the 5G access network, while a second UPF can be deployed to provide connectivity to the external data network. The N9 reference point defines the connection between the two UPF. Similarly, the N14 reference point defines the connection between two AMF. The N26 reference point can be used to connect an AMF within the 5G core network with a mobility management entity. Within the 4G evolved packet core, this reference point is used for interworking between 4G and 5G. For example, inter-system handovers. When using 3GPP Next Generation Radio Access Network, NG-RAN, user plane data and control plane signaling are transferred between the UE and NG-RAN using the UU-Air interface. Our next topic is service-based system architecture. The 5G system service-based architecture are presented in a figure shown on the screen. This architecture specifies a set of network functions, NF, and a common bus which interconnects those network functions. The service-based architecture is applicable to the control plane section of the 5G core network. The reference point architecture remains for the user plane section of the 5G core network. The functionality associated with each network function is described in later part of this course. The Network Repository Function (NRF) plays a central role within the service-based architecture. Network functions register the services they offer with the NRF. They then use the NRF as a database to discover the services offered by other network functions. The following three mechanisms are used. First, service registration allows a network function to register with the NRF and inform the NRF which services are offered. Second, service discovery. Allow a network function to discover other network functions and the service they offer. Third, service authorization. Ensure that a network function is authorized to use a service provided by other network functions. The service-based interfaces connecting each network function to the common bus are labeled as NAMF, NSMF, NPCF, etc. Services are provided and consumed using these interfaces. Network functions signal to each other using Hypertext Transfer Protocol version 2 (HTTP2) specified by the IETF. 3GPP describes the use of HTTP2 within the context of the service-based architecture. The HTTP2 protocol defines methods for signaling between network functions. For example, HTTP2 methods include POST can be used to request a service from a network function. GET can be used to retrieve data from the network function. PUT can be used to create new data at a network function. Patch can be used to update existing data at a network function. Delete can be used to delete data at a network function. As an example of the services offered by the network function, there is the table that represents the services offered by the Access and Mobility Management function (AMF). The AMF provides connectivity towards the access network, so the AMF provides an AMF communication service to allow signaling towards the base station and the UE. The N1-N2 message transfer operation can be used to request the AMF to forward a message to the base station or to the UE. For example, the short message service function can use the service operation to forward an SMS over non-access stratum signaling towards the UE. This is initiated by the SMSF using an HTTP POST method to send an N1-N2 message transfer message to the AMF. This message encapsulates the SMS to be forwarded to the UE. If a UE is in idle mode, then the NAMF-NT service can be used to request the AMF to page the UE and consequently bring the UE into connected mode. For example, the SMSF can use the enable UE reachability operation in advance of using the N1-N2 message transfer operation if sending an SMS to a UE which is in idle mode. NAMF Event Exposure Service allows network function to subscribe to notifications of specific events. For example, the Unified Data Management UDM can use the subscribe operation to request the AMF to provide notifications regarding the location of the UE. Similarly, the AMF can provide notifications regarding the registration state, connectivity state, or reachability of the UE. The service-based architecture represents a move towards a cloud implementation of the core network. Legacy core networks have been deployed using separate hardware for each network elements. Newer core networks have been deployed using virtualized network elements to allow multiple network elements to operate using shared hardware platform. A virtualized solution can provide fault tolerance by allowing the software to switch between a hardware platform in case of failure. A cloud implementation is expected to increase flexibility, agility, efficiency, and scalability relative to previous solutions. Flexibility is particularly important for 5G due to a wide range of target applications. Agility allows new service to be introduced with minimal efforts and short time to market. The 5G core network is also designed to support connectionless services, that is, services which allow data transfer without a connection being established across the 5G network. Connectionless communication is a requirement for massive machine type communication (MMTC) to support the very high density of devices. Here I conclude this course. Hope you understand all the concepts clearly. Meet you in the next course.
So what are you waiting for? Join us for the course and do subscribe to our YouTube channel and don't forget to press the bell icon. Also, if you like our videos, don't forget to hit the like button and share our videos.